Hello there. So this is video number 2 of section 1.7, where our focus is on linearly independent and linearly dependent vectors. And in this mini lecture, our goal is just going to be to sort of focus on a few different types of instances where maybe we can just look at a set of vectors, kind of eyeball a set of vectors, and be able to tell, okay, that set of vectors is linearly dependent. So the focus of this video will be to really talk about and understand what linearly dependent sets of vectors look like. We know what linearly independent sets of vectors already look like. They only have the trivial solution to the corresponding homogeneous equation. And remember, none of the vectors can be written as a linear combination of the others. But what do linearly dependent vectors look like? So first things first, I want to start off with this example where we're given two vectors in R2, and we want to know if they are linearly independent. So generally this problem with two vectors is not horrible because there's not much that can really happen with two vectors. So let me show you what I mean. Notice if I were to do 3v1 plus v2, well, 3 times v1 is the vector 9, 3. v2 is the vector negative 9, 3. And so I get that. And so the answer very quickly is no. They are linearly dependent. Right? Because I found a non-trivial solution. To this homogeneous equation. That is where the constants here 3 and 1 are non-zero. So notice here that because we've only got two vectors we're working with, if we were to rework this equation, we would get 3v1 is equal to negative v2, or maybe negative 3v1 is equal to v2. Right? And of course, that's what the definition of linearly dependent tells us, is that I should be able to write one as a linear combination of the others. But since there's only one other one, we can actually take this a step further and say that a set v1, v2 of two vectors in Rn is linearly dependent if v1 and v2 are scalar multiples of each other. Right, and so what this means, of course, is that I can find some scalar. Here in this example, it was negative 3, such that if I multiply v1 by that scalar, I get the exact vector v2. But notice this also implies that v1 is a scalar multiple of v2, right? Because I could just multiply v2 by negative 1/3 and get v1. And so this actually then generalizes to any pair of vectors of any length, so not just length 2, it could be length 3 or more. That is, a set of two vectors is only going to be linearly dependent if they are scalar multiples of each other. And so what's nice is that if you're just given a set of two vectors that you have to sort of figure this out for, you can usually determine this fairly quickly, right? That is, like you can kind of just eyeball the two vectors and say, okay, are these multiples of each other, yes or no? And determine if they are linearly independent or dependent. So we have a nice generalization, which I talked about last video, for sets of more vectors, right? So if we have more than two vectors, unfortunately, it's not generally not as easy to, I guess, eyeball this one in that way. So let me write this down while I drop my eraser. So a set of p vectors index them like this, v1 through vp of vectors is linearly dependent if one of the vectors or we'll say at least one of the vectors say v sub I can be written as a linear combination of the others. So I want to say a few things about this before moving on. And so that is v sub I is equal to C1 times V1 plus, well, it's not going to be written as a C linear combination of itself. So what this is saying is that in this set, I can take some vector v sub I and write it as a linear combination of all of the other vectors. So notice specifically in this sum, I'm leaving out v sub I on the right-hand side. So a few things about this. If you have 3 or more vectors, this idea tends to be a fairly bad way to determine if, or unreliable, I should say, way to determine if a set of vectors is linearly dependent. That is because generally once you get to 3 or more vectors, it can become very, very difficult to actually find this. I think we'll sometimes refer to this as a linear dependence relation. So I'll sort of say this is a dependence relation. It can be very hard to find an equation like this. And as we start to look at more examples, you'll definitely start to see that it can be very hard to guess the correct scalars, C1 through CP, you'll need for that. And so generally, the more reliable way of determining if a set of vectors is linearly dependent or independent, assuming that you don't have one of the other ways, which we'll talk about here in a sec, is just to set up the matrix and row reduce like we did in the first video in this section. The other thing to note is that not all of these scalars has to be positive, or has to be non-zero. So I'll give you one example here of what I mean by that. So let's say we had a few vectors in R4. So let's say we had this set of vectors in R4. It turns out that these 4 vectors are actually linearly dependent, and it's not terribly hard to find the dependence relationship here. We could say that V1 is equal to 1 times V2 plus 0 times V3 plus 1 times V4. And so why I'm doing this example is to sort of notice that, V4 should be, that should be V4. Now it's a dependence relation. And so why I'm using this example here is to point out that, notice V1 can be written as a linear combination of the other 3, but I don't necessarily have to use each of the other 3 vectors to get to V1. So V3 doesn't really help me get to V1, but I can still write one of the vectors as a linear combination of some subset of the others. And actually, I'll change the this of a subset of the others. And so not all of these C's need to be non-zero, just at least one of the C's needs to be non-zero, and these vectors are linearly dependent. So as long as, again, we sort of have this like single vector which can be written as a linear combination. The others, always linearly dependent. All right, so that's one way of determining linear dependence. This idea works very well if you have two vectors or maybe a few vectors which you can eyeball. So like the example I just erased with the 4 vectors in R4, sometimes you can just eyeball like what the dependence relation is going to be, and so you can just kind of figure it out from there. Like I said, generally a bad idea to try and start guessing scalars. I think that the always safe way is to set up the matrix, row reduce, and verify that you do get a free variable. But anyways, moving on from that. Now we want to look at another case. I'm going to give you 3 vectors in R2. And we want to determine if these are linearly independent. So I'm going to actually work through it's a relatively short row reduction. I'm going to work through the row reduction here just so we can see this example. And I think looking at the row reduced matrix will give us a very good intuitive idea of the next fact I'm going to state. So let's pretend we're going to do this the usual way. We set up our matrix. We want to row reduce and count the number of pivots in our matrix, or equivalently count the number of leading ones in our row reduced matrix. And so I might move a little quicker through this row reduction. It's not terribly hard. I'll write out all the steps. But just to get through this, the row reduction here is not the main. The row reducing this matrix is not really my main goal with this video. Ooh, my computer is about to die. I'll be right back so that I don't lose this. All right, I'm back. All right, so now we're going to divide -1/3 by row 2. Now we'll do -2, row 2 plus row 1. And that leaves us with the following row reduced echelon matrix. All right, so given that this is the row reduced echelon matrix, we have 2 leading ones, meaning we have 2 pivot variables or 2 non-free variables, but we do have 1 free variable because remember we have 3 columns, 3 vectors, 3 variables. Again, I've sort of started to drop the last column of zeros that would normally be there if we were considering the homogeneous equation that corresponds to a vector, determining linear independence. But again, you can imagine if you want that there's this column of zeros at the end. But so we can say here 2 leading ones and 3 vectors. And this would imply linearly dependent. And so what I want to get from this example before we state this as fact is notice that from the start, these three vectors were doomed. Because notice that if you think about the system of equations that these three vectors represent, remember, each equation represents sort of one row going all the way across. Right? So if you think about the homogeneous equation system of equations you would have set up a system with two equations and three variables. And remember, anytime we have more variables than we do equations, we're going to have a free variable. So translated to vectors, anytime I have a set of vectors that contains more vectors than the length, so here I had three vectors, and all of the vectors were of length 2. If the number of vectors I've got is greater than the length of all of the vectors, that set is always going to be linearly dependent. And so this will be our second to last big fact. We'll state it as a theorem. This pops up as Theorem 8 in section 1.7 of your book. And so, again, you can sort of think of the reason for this, or the proof behind this, as being the fact that we have more equations, right, or more variables, excuse me, than we do equations. So you can think of like each one of these vectors as representing the coefficient attached to a variable, or the coefficients attached to a variable, and we have n equations, and if we have more variables than equations, we're always going to have a free variable. And so, like, for example, we would know that the set, right off the bat, without having to find the linear dependence relation, we would know that this set is linearly dependent because of this theorem. Because here we've got 4 vectors and 3 each of length 3. All right, so I want to do one more example, and then we will be done with this section, actually. And it's interesting, so I was writing this, using your book, and I find it interesting that the book puts this example last, because this would seem like sort of the first example to consider. So we want to determine if these 3 vectors are linearly dependent. So we'll say determine if these 3 vectors are And so this is sort of another one of those things that becomes trivial, because notice we've got the 0 vector, and the definition of linear dependence, I mean, it counts for the 0 vector, but like the 0 vector is like the thing that always kind of cheats these definitions. And so the answer is yes. And you can just pick your favorite number. My favorite number is 2. But really, any number would work. And notice that this linear combination, well, it's not the trivial solution, right? Because I've got a non-zero value here. But this still equals 0. And so any set of vectors containing the 0 vector is linearly dependent. But it's a little iffy, right? Because, like, saying, well, any vector can be written as a non-trivial combination of the other, it feels cheating in a way. But by definition, it technically is linearly dependent. So anyways, that wraps up this section. So what you should get from this section, how to check if a set of vectors is linearly independent. To do that, you always have to row reduce and verify that you have as many leading ones as you do variables. And some ways to check if a set of vectors is linearly dependent. Remember, there's always a foolproof way to do it, to also just row reduce and verify that we have a free variable in our augmented matrix. But some of the things I've introduced here you can use sometimes to very quickly determine, right? So especially Theorem 8 is a very nice one. But they also shed a little bit of light on like how this works, right? I think it's very interesting that, you know, as long as we know that I have more vectors than I do entries in the vectors, that we always get some sort of dependence relation among the vectors. That once the number of vectors hits the length, in a way the vectors sort of can't escape each other. So anyways, that wraps up this section. Next section, we're going to start something fairly different. So be on the lookout for that.